Let's suppose that we have a large circle centered at the origin, and inside of that circle is a disk of radius 1. The circle has radius 9, and this disk is centered on the non-negative x-axis. So this point here is some r comma 0, where r is between 0 and 8, not including 8. There will be 2 points P and Q, which will be independently and uniformly at random selected on the circle. If we draw the chord between those 2 points, the chord will either intersect the disk or it won't. In this case, it does not intersect the disk, but if point Q were drawn to be this point instead, then of course the chord does intersect the disk. For any particular placement of this disk, which is to say for any particular choice of R, there is going to be some probability that we could calculate that the chord generated by the process I mentioned will intersect the disk. And what we would like to do is minimize that probability. Choose a particular value of R that minimizes the probability. Here's the full problem statement if you'd like to pause the video to read it. For starters, let's suppose that point P is selected to be this point here, which in general will have the coordinates 9 cosine of theta, 9 sine of theta, where theta is a random variable with a uniform distribution on 0 to 2 pi. If we draw tangent lines from P to the disk and look at where those tangent lines intersect the circle, we can clearly see that this red arc between those 2 points on the circle are precisely the points where if Q is one of them, the chord will intersect the disk, and if Q is not one of those points, then the chord will not intersect the disk. So we would like to find the probability, if we pretend that we already know where the first point is, we'd like to find the probability that the second point, Q, is going to be on that red arc. Finding the probability that this happens is easy. We can just draw the angle right here and measure it. If that angle happened to be 1/10 of a full circle, let's say, the probability would be 1/10 that a point would be chosen on that arc. In general, if this angle measures phi radians, then the probability that Q is on the arc is phi out of 2 pi. If you remember your geometry well, you will know that there is something called the inscribed angle theorem, which is very helpful here. The inscribed angle theorem tells us that this red angle is precisely double the measure of angle P. So if we can find angle P, then we can find phi. Furthermore, if we look at the angle bisector of P, the angle bisector passes through the center of the disk. If we then draw from the center of the disk a radius perpendicular to the tangent line, we have ourselves a right triangle in green. That right triangle has sides of length 1 because the radius of the disk is 1, and this hypotenuse has a length that we'll go ahead and call d of r comma theta. It's a function in terms of r and theta, but we can determine exactly what that function is because it's just the distance formula using 2 points that we've defined. If we can use trigonometry to find this little green angle here, then doubling it will give us angle P. because this initial hypotenuse, this green ray that forms the hypotenuse, was the angle bisector. So doubling it will give us angle P, and then doubling it again will give us phi. Here's that green triangle again, and its side lengths. To calculate this angle, we just recognize that whatever the angle is, we know what sine of it is. Sine of that angle is going to be this. And so arc sine of that quantity is the green angle we're looking for. If we double it, we get angle P, and here's angle phi. By doubling again, there we are. And therefore, the probability of a success, where let's suppose that when I say success, I mean that the chord we generate by this process intersects the disk. The probability of a success given a fixed value of P, or equivalently a fixed value of theta, which in turn tells us where P is on the circle. This probability, we said before, was phi out of 2 pi, and so it is simplifying this quantity. Now, of course, we don't really care all that much about the probability of a success given theta. We just want the unconditional probability of a success. So to determine that, we're going to use the law of total probability. By the law of total probability, we can say that the probability of a success is the following integral. It's the quantity we just found times the probability density function of theta d theta. So in our case, we can copy over the values from the previous slide. The probability density function on theta is 1 over 2 pi, because remember, theta is a uniform random variable from 0 to 2 pi, and that's where we will integrate. And finally, factoring out some constants and simplifying, here's our answer. This integral is extremely difficult to calculate, and so we will not do that. It's virtually impossible. But luckily, we were not asked to calculate any probability. We were just asked to find the value of r, which minimizes this quantity. Notice how our function d is a function of 2 variables, and we're integrating over only one of them. So this result is a function of r. I'll call it f of r, and I'm looking to minimize f, which means I should think about taking derivatives of this. What I would like is for f prime of r to be 0, which would make r, this particular value of r, a min or a max, and I would like the second derivative of f to be positive. Before we go computing these derivatives, I actually skipped the part where we determined exactly what this function d is. We're going to need to know what d is as a function exactly, and we'll also want to know about its derivatives before we start taking derivatives of this whole thing. So let's do that. d of r comma theta we defined to be the distance between point P and the center of the disk, and we had the coordinates of those 2 points. So d is going to be found using the distance formula. It's the square root of the squared difference in the x values. Those x values are these two, plus the squared difference in the y values. And of course, sine squared plus cosine squared is equal to 1. So I can group these two together and get my final result for D. It's easy to check that the first derivative of this function with respect to r is the following. You conveniently end up getting the function d inside of this derivative. And we can factor out 2 on top and bottom to get this result. And as for the second partial derivative with respect to r of our function, we can use the quotient rule to get this. It ends up being defined in terms of the first derivative and the function itself. I'm going to substitute in just a moment the value we found earlier for this first derivative. It contains a factor. In fact, the entire numerator is r minus 9 cosine theta. So I'll write this as a squared quantity. Now here's a really nice fact about the second derivative that we just calculated. We can easily show that this is non-negative. Clearly the denominator is non-negative. It's a distance which is being squared. Just the fact that it's being squared at all makes it non-negative. So whether the fraction's non-negative really just comes down to the numerator. The reason I know that this numerator is non-negative is because we can simply rearrange this, add the right term over to the right, and multiply both sides by the function d to get this relationship. And this is true by the Pythagorean theorem, because remember that d is the hypotenuse of a triangle. If we go back, d was this distance between P and the center of the disk, and r minus 9 cosine theta is actually just the distance in the x direction between these 2 points, because r is the x-coordinate of the center of the disk, and 9 cosine theta is the x-coordinate of P. So I am comparing the square of the function d, which is the hypotenuse, to the square of this short side. So this is actually true, And so it follows, by going backwards, that this numerator is non-negative. And so the fraction is non-negative. Some solutions will make use of this. Our solution won't, but it is a nice fact to verify. Now that we have some of the derivatives figured out for d, it's time to start taking derivatives of f. We can use something called Leibniz rule to find the first and second derivatives. We can say that the derivative of this integral is equal to the integral of this partial derivative. Essentially, you can swap, in some cases, the order of the derivative and the antiderivative. The integral of arcsine is 1 over the square root of 1 minus x squared. But of course, in this problem, x has been replaced by the function 1 over d. So it is 1 over d, which we will square. And then by the chain rule, we're going to multiply by the derivative of whatever replaced x, which was 1 over d. Here's what that derivative should be. Recall that we've calculated what this derivative is, so to make things a little nicer in a certain sense, I'm going to get rid of partial derivatives of d and replace them in terms of the functions of d. And I'll put that minus sign out front. I'll just factor out entirely. And by Leibniz rule, again, we can calculate the second derivative. Now, this is going to be a little bit monstrous, but derivatives are easy after all. This will just be a little bit of a grind. I'm going to skip ahead to save time. This is the second derivative. Something that would be really, really convenient would be if this large integrand were never positive, only negative or 0. Because if that were the case, then when we integrate over a function which is, let's say, less than or equal to 0, that result will be less than or equal to 0. And then when we multiply by this negative quantity, it will become greater than or equal to 0. Always, for all values of r. And that would help us achieve this goal, this condition for a point being a minimum on a function. I'll show you a proof that this is the case, which is similar to what we did for the second derivative of d. I would like for this part of the numerator to be less than or equal to the other part of the numerator, so that when I subtract them, I get a quantity less than or equal to 0. I'll once again rewrite this first derivative with respect to r, like so. And remember that we cleverly discovered that this is less than or equal to d squared. So this whole product is less than or equal to the following. I will begin solving for D, and it'll actually turn out that we don't have to go all the way. Just subtract the left term on the right-hand side over, and notice that the left-hand side is now less than 0, less than or equal to 0, and 0 is less than or equal to 1 over this square root, since square roots are non-negative. I know that this is true. And so working our way backwards, I know that this is true, and I know then that the integrand is non-positive, less than or equal to 0. So the integral is non-positive, and when I multiply by this negative constant, it becomes non-negative. And so I can say that f double prime of r is non-negative for all values of r. We haven't even used the fact that r is limited to these values. This is actually true even if I allowed r to take on negative values. And the reason why I know that I could go further and say that f double prime is actually strictly greater than 0 is the fact that this inner function, this integrand, is not identically 0. So we have met this condition for minimums. And the fact that this is true for all values of r means that if I can find even a single value of r which satisfies the first condition, that will not only be a local minimum, but it will be a global minimum. So all I have to do is find a single value of r which satisfies that condition above. Finding a value of r where this integral is 0 is actually simple. Just consider the case where the disk is located centered at the origin, which is to say that r equals 0. When this is the case, point P, which we select, will always be 9 units away from the center of that circle, of that disk, no matter what the value of theta is. Therefore, in this specific case, d of 0, theta is constant. Therefore, all of this is just one big constant, which I can factor out. Which means that this equals some constant times the integral from 0 to 2 pi of r minus 9 cosine theta, except r is 0. So it's just minus 9 cosine theta. And in fact, I could even absorb the negative 9 into c, so it's the integral of cosine of theta, which of course, from 0 to 2 pi is equal to 0. And we have our answer. F prime of r equals 0 in this case. So r equals 0.